All right, everyone. In today's video, we're going to be talking about naming compounds, which is this new stuff coming up in Learning Module 3. You might be kind of familiar with how these things are named from the stuff that you learned in 7th and 8th grade, but it might be a little unfamiliar as to how they actually get to the conclusion that they've gotten to. So I wanted to try to break it down as easily as possible to give us kind of a flow chart kind of feel of how to get from a compound that you're given to the name, or from the name to the compound that you're looking for. So the first thing to note is that when we're creating compounds or molecules, we're creating bonds, right? So we're looking for certain types of bonds between those elements when we are trying to name what's going on in that molecule or compound. So the first thing that we need to do is actually determine what type of bond is present. We can do that very easily. Okay, all that we need to do is identify what types of elements are present in that bond. So there's two types of bonds that we're going to primarily be dealing with. First is ionic bonds, which we saw a glimpse of in Learning Module 2, and the second is covalent bonds, okay? These two types of bonds happen between atoms in order to create these molecules that we see around us. So starting with our left side of our flow chart. First, we have covalent bonds, all right? Covalent bonds are made up of two atoms or more that are just nonmetals, okay? So a covalent bond is made between a nonmetal and a nonmetal. So covalent bonds in a covalent molecule, right, would be happening between two nonmetals, and that's it. Remember, on our periodic table, all of the nonmetals are going to be located over here on the left side towards the upper right corner. As you can see here, those are labeled in teal above the purple. So these are all of our nonmetals over here. So if we're looking for a covalent bond, we want to identify those as elements over here on the left side. If it is a bond between two nonmetals, then we get to name this bond or this compound or molecule as though it was a covalent bond, meaning that all that we need to do actually is look at the number of atoms and use the correct prefix. So naming covalent bonds is relatively simpler than ionic bonds, as you see behind me. So covalent bonds, first we need to know how many atoms there are in this molecule of each element. And then we can simply name it based on how many there are. So if we look at this first example here, in this first example, we have two elements present. The first element is C, which stands for carbon, and the second element is O, which stands for oxygen, okay? So the very first thing that I'm going to do right now, just to kind of keep track of what I know, is I'm just going to go ahead and write out the elements that I have here. So here I have carbon and oxygen, okay? Now, these are the names of the elements, but this is not the name of the actual molecule. So in order to change what we have here to be the name of the actual molecule, we have to add and adjust what we have. So the carbon here, we are given one carbon in this molecule. So since there's only one carbon, we're going to leave carbon just the way that it is, all right? As you'll notice up here, the prefix for one is mono. But if the first element of your compound is the one that there's only one of, we never put mono at the beginning, okay? So we only ever use mono on the second word of our name. That's only true with mono, okay? So carbon, there's only one of them, so we're just going to leave that the way that it is. Oxygen, though, there are two of them. So because there's two oxygens here, we're going to grab our prefix for two, which, as you can see here, is di, all right? So the prefix for two is di, and those are prefixes, right? Which means they come before the word. So the prefix di is going to come right here before the word oxygen, all right? Before the name of that element. Now, this might look weird. Wait, I've never heard of a compound named carbon dioxygen, but you might have heard of a compound named carbon dioxide, right? So carbon dioxide is the common name, and that's because whenever we're naming covalent compounds, we always need to take the end of the second element, so this oxygen the ending of this is going to change to IDE, or IDE. So for oxygen, we remove the YGEN, and that becomes IDE. So this creates the name carbon dioxide. All right? So same idea with the next example. Let's go a little bit faster. In this molecule, we have 2 hydrogens and 1 oxygen. So I'm going to start off with hydrogen and oxygen. Okay? So we have 2 hydrogens though. So this hydrogen right here is going to need a prefix since there's 2 of them. My prefix for 2 is di. I'm going to bring that right down here in front of hydrogen. Dihydrogen. Now, we don't change the ending of the first word of the name. We only change the ending of the second word of the name. But we'll see in this case, we only have 1 oxygen. So remember I said mono. We do use that on the second word. So this, rather than being oxygen, it's going to need the prefix mono. Okay, mono. And then the oxygen, remember, the ending changes to IDE. So this becomes dihydrogen monoxide. Okay, dihydrogen monoxide. So the mono is from the prefix, the ox is from oxygen, and the IDE is the ending that we change it to. Last example, we have 2 elements again. We have B, which stands for boron. So we have 1 boron, and we have F, which stands for fluorine. We have 3 fluorines. So in this compound here, we have 1 boron. Remember, we're not going to put mono at the beginning, so that just stays boron. And we have 3 fluorines, so I need to grab my prefix for 3, which is tri. So I'm going to bring tri down here, and then my ending is going to change to IDE. With fluorine, it's a little bit easier than oxygen. That just changes to fluoride instead of fluorine. Okay? And that's how we name our covalent compounds. We simply have to look at the number of atoms that are present in order to get that. Now, we come over here to this side. Things get a little more complicated, a little trickier. So I'm going to turn this a little bit. So if our bond is actually an ionic bond, okay, an ionic bond happens between a metal and a nonmetal. So that's going to be a bond between an element from the left side of our periodic table, anywhere in this big old left chunk, and 1 element from over here on the right side, our nonmetals, okay? So one from the left, 1 from the right. That's going to create our ionic bond. Now, that can show up pretty much in one of 3 ways. Pardon. First, it can be the kind of what we say normal ionic bond, which is going to show up as a salt, okay? The normal ionic bonds will show up as salt, which we talked about in the last video. These salts or normal ionic bonds are going to be the most straightforward to name. The easy part about these is that ionic bonds, we never use the prefixes. So prefixes only stay on this side with the covalent bonds. We never use them over here with the ionic bonds. So simple for us, all that we need to do for a salt, we don't have to worry about the number that are present. All that we have to do is name what we have. So in this example here, we have a calcium atom. So we have calcium. Oh, I cannot spell. The I comes before the U, everybody. We have calcium and we have bromine. So we have calcium and we have bromine. Now the thing that is similar between the ionic and the covalent bonds is the ending, which we need to change in both scenarios. So rather than this being calcium bromine, this needs to change to IDE, so it becomes calcium bromide, okay? As you can see, there's another example below that, which this way we're actually going backwards. We're given the name, and we want to know what does the formula actually look like. So let's go backwards on this one, okay? On this one, we have lithium, all right? If we have lithium, the symbol for that from the periodic table is Li. And then we have oxide, which we recognize from this side as oxygen, okay? So we have Li and O. But now is where the important part comes in. That can be a little tricky, okay? Li and O, we have to make sure that their charges that we talked about in the last video, we have to make sure their charges match and even out to 0, okay? So lithium, if we check where lithium is on the periodic table, we will see it is in the very first column, okay? If it's in the very first column, we remember the first column has a charge of +1. Oxygen, though, is all the way over here in the 16th column, okay? The 16th column, which we remember has six, there you go, valence electrons, is going to have a charge of -2. Okay, so oxygen is going to have a charge of -2. Now, if we look at these numbers, we add those together, that actually doesn't equal 0. So if those don't equal 0, just like we did in our last video, we need to do the crisscross method, okay? Or we need to take the charges and move them to be our subscript down here. So crisscross method, we take the 1 charge from lithium, the 1 comes down here by oxygen. Remember, we don't write 1s though, it's just going to remain a blank. So that 1 came down here and we remove it. And then the 2 is going to come down here on lithium. So the 2 from oxygen gets placed on lithium as a subscript, and then we can get rid of that charge. So now this is the actual formula for lithium oxide. There's actually 2 lithium atoms for every 1 oxygen atom, okay? So that's how we go backwards. Now, if we look then in the center, we have a new scenario, all right? Still want to make sure that our bond is an ionic bond, so still between a metal and a non-metal. However, in this case, if we have a transition metal as part of our compound, then something special has to happen, okay? We can't just go straight forward like this. We have to identify an extra piece of information here. So if we have a transition metal, which we will remember is the middle section here in orange, the middle section of the periodic table here in orange, the transition metals are going to give us different charges depending on what they're connected to. So you have to use them in context. All right, we have to look in context. So the first example here, we have CuCl2. We're going to go ahead and start just like we did it with all the other ones, of course. Let's just write down the elements that we know that are there. The first element we have is Cu, which on the periodic table corresponds to copper. Okay, Cu is copper. The second element that we have is chlorine, Cl. So that is going to be chlorine. Now, first, we know there's one thing right off the bat that has to happen with all of these, change the ending, right? So first we can very easily do that because that's very apparent. We can change the ending to IDE. So now we have copper chloride, which looks very similar to calcium bromide, right? So that's great. That puts us in the right position. However, we need to identify something else about this compound now, which you might see in this example right here. There's something new. The Roman numerals, okay? These Roman numerals here are describing the charge of the metal in that compound. So in this case, copper is the metal, right? The Cu is the metal. And we need to know, okay, what's the charge of that metal? Since it can change, right? It can change depending on what it's connected to. So how do we figure that out, Alanson? What are we going to do? Well, let's look at what we do know. We do know the charge of chlorine, Cl. If we look on the periodic table, chlorine's in the 17th column. All those elements in the 17th column we talked about have a charge that we know, which is -1. So each chlorine atom has a charge of -1. We notice, though, there's 2 of them. So if there are 2 chlorines and each one is a -1, then in total, the chlorines give us a charge of -2. If you'll remember from our examples above, Our goal here is to make sure that our charges cancel out. So if the chlorines give us a charge of -2, then the copper have to cancel that out with a +2, okay? So the chlorine have to cancel out with a +2. So now since copper has +2 charge, what we can know at that point is the Roman numeral, which corresponds to that number. So if the charge on copper is the number 2, then we put the Roman numeral 2 in the middle between the metal and the non-metal. Okay, I know that's an extra step to add, but we have to identify the charge of that element that we are dealing with in the front, okay, that metal. So I'm going to remove those charges just so they're not clogging up space. If we look at the next example, we can look at this backwards, just like we did in the last one, okay? So now if we look at this backwards, we have iron 3 oxide, okay? Iron 3 oxide. So the first thing that we want to find out is, what's the symbol for those elements, okay? The symbol for iron from the periodic table is Fe, and the symbol for oxygen, remember oxide corresponds to oxygen, is going to be O, right? We know that. Pretty easy. Now, there's some information here that we don't know, right? But there's also some information that we do know. So this Roman numeral right here gives us a hint. Ooh, what's the charge of that metal? So this Roman numeral tells us the iron has a +3 charge. Okay, iron has a +3 charge. The Roman numeral always describes the metal. So if the iron has a +3 charge, and we look at our periodic table at oxygen, which we know, again, because it's in the 16th column, has a -2 charge. Now we know the charges of both of these things. So how are we going to figure out how many atoms of each we need? Hello, the crisscross method again. Boom, it's hitting us in the face. So we take our +3 charge, we're going to take the number 3, bring it down here on oxygen as a subscript. That will go away. And then we're going to bring our -2 charge, take that number, bring it down here, put it on the iron, take away that charge that we had written there. And now we have the formula, the correct formula for iron 3 oxide. There's 2 iron atoms for every 3 oxygen atoms. And there you go. There's one last scenario with our ionic compounds, though, okay? One more. I know this has been a lot. The one more, though, is very easy because of the way that these names are presented, okay? The last one are these things called polyatomic ions, okay? Polyatomic ions are these chunks of atoms that never like to leave each other, okay? And you can see that here in an example on number 3. MgSO4. That SO4 right there is what we're referring to as the polyatomic ion, okay? The reason it's called polyatomic ion is because if you break down the word, it's exactly what it means. Poly, which is the prefix for many, atomic, atoms, and ion, ions, right? So many atoms that are ions, right? Pretty simple. Here we have, in this chunk, many atoms that are ions that stick together, okay? So these, since they always stick together, we actually name them one thing, and that name never changes, okay? So that's very easy for us in terms of what we need to know, and I'm going to tell you which ones are the ones that we want to just know right off the bat, okay? But to look at our examples first, we're going to start just the way that we did, right? We have an Mg right here. Mg on the periodic table is magnesium, okay? Magnesium. Magnesium is going to here be connected to this chunk called SO4, which we refer to as the polyatomic ion sulfate. Okay? Sulfate. So the polyatomic ion, in this case, that SO4, is called sulfate. All right? Now, again, like I said, the beauty of this, the sulfate name never changes, okay? SO4 is always called sulfate. So anytime we see that chunk, SO4, it's sulfate. Okay, that name's not going to change no matter how many of them there are. If you've got 7 sulfates, it's still called sulfate. Okay. Now let's look at this last one. See if we can do it in reverse. So here again, we have this metal here, nickel. Okay, nickel. The symbol on the periodic table is Ni. Okay, the symbol on the periodic table is Ni. And we have a Roman numeral here. So it's a transition metal. So that means that we know that the charge of nickel is going to be +2, right? +2. And then we have this guy here, chromate. Ooh, I do not know what chromate looks like. What am I ever going to do? Well, right now in the beginning, when you're practicing things, look it up, okay? If you don't know what the formula for chromate is, look it up here in the beginning as you're trying to practice these things, and then you'll get more familiar with it as you see it more, okay? Chromate is a chunk of chromium, Cr, and oxygen, and 7 of them to be specific, okay? Oh, my goodness, I'm so sorry, not 7. That's supposed to be a 4. Okay, sorry, 4 oxygens, not 7. So nickel with a +2 charge, and chromate with a, what charge does it have? Well, easy for us, in this case, chromate is always going to have a 2- charge, okay? A 2- charge, which again, you can find out from looking it up at this point because we're still in this practice phase, okay? So if nickel has a charge of 2+ and chromate has a charge of 2-, how many of each do we need? They already balance each other out. So we don't need additional either of them. So we can just remove the charges, and our formula simply is, I'll just move this over to compact that. Our formula simply is NiCrO4, okay? So polyatomic ions, although they are very simple in terms of the name never changes, we do want to make sure that we're familiar with some of them, okay? So some of these polyatomic ions that we want to get more and more familiar with as we use them are going to be PO4, 3-, that is known as phosphate. We're also going to want to be familiar with NO3-, that is known as nitrate. We're going to want to be familiar with CO3, 2-, that is carbonate. And also that's a bad S. And also SO4, 2-, which is known as sulfate. Okay? So those are the four big polyatomic ions that we're just going to want to know off the top of our head. We're not going to be responsible for many more other than these in our efforts with tests and such, okay? So these are the 4 that Dr. Lottie wants us to be comfortable with. So that about wraps up our naming compounds. I know that was a lot of information and a lot of things. What's gonna be key with this is gonna be practice, okay? So the practice that I'm giving you is gonna be absolutely crucial. So please make sure that you take time to try that out. And as you encounter these new compounds and this new language, basically, if things don't click, if things don't make sense, reach out to me, all right? Thanks so much, y'all.